Thank you very much. This is kind of like Janet Jackson, really interesting. Don't worry, I'm not going to do like a wardrobe malfunction or anything like that. So, as I think he said, I'm Thomas Watson. I'm WA7SON on GitHub. So, if you have any questions during my talk or after that I didn't talk about or answer, just feel free to give me a shout on Twitter. And I'm just going to tweet my slides. I have them here. So you can even, there we go. So I tweeted my slides. So if you go to Twitter, you can see all my slides there. Or there's a link to it, but you know the drill. So, so my talk is debugging Node.js in production. So when things go wrong, this is the talk you need to refer to. And the plan is today to talk about how you debug CPU-intensive code. That's something that have the potential to really slow down your app in ways that is really hard to figure out why. Also, we're going to go through debugging crashes that you can't really figure out by just looking at the stack trace. And then, of course, memory leaks, which also can be a bitch to figure out. And we're going to, hopefully, if you have time for that, end with a Q&A. So, who am I? And why am I talking to you about this? I'm an open source developer. I put all my code on GitHub under Watson. And I'm the Node.js lead at Upbeat. Upbeat is a company that works with performance monitoring of production systems. So this is something that I basically work with every day. And then I'm a member of the Node.js diagnostics working group under the Node Foundation, where we also work on the next generation of tools that are going to help Node developers debug and monitor their Node applications. So this talk is heavily based on work that a guy called Brendan Gregg he did or is doing. He's working at Netflix currently, but he did a lot of stuff for Sun Microsystems back in the days, where he built some tools that we're going to look at. And he actually also worked at Giant, so he knows a lot about Node as well. And as you can see, he received recently a LISA Outstanding Performance Award for contributions to the field of system administration, particularly groundbreaking work in system performance analysis methodologies. So, in any case, why is it important to be able to debug Node in production as opposed to your development or staging environment? It's important because sometimes bugs and performance issues only appear in production. You have no way of reproducing them locally, and the only source of the problem you have is in your production system. So that's why that is important. And why is it then harder? Why do you need to have a talk about it? It's because a production system have real users. It's important that it's online, and you can't just enable debug mode and go step through a debugger in your production code, because you would hold the entire system. So it's kind of like this black box that you don't really want to touch too much, because you don't want to impact the performance of it, and you want it to be online all the time, of course. So as I promised in the plan, the first thing we're going to look at is CPU-intensive code. So what can slow down your app? So I wrote single-threaded in parentheses, because that's not really a cause of slowdown, but it has a lot to do with the problems that we have and how we're going to attack these things, and what can slow down your app. So CPU-intensive code, of course, can slow down your app. We talked about that. Slow I/O can also do that. So you have an incoming request, and it's talking to the database, but the database is really slow, the network is really slow, or something like that. So it takes a long time for the client to get a response back. Then you have a problem where your event loop, because this is single-threaded, Node is using an event loop to try to have all these requests that are coming into your application running at the same time. But if you get too many requests, too much stuff that you queue in the event loop or something like that, it can't keep up and you get saturation. So that can also slow down your app. Of course, running out of memory is also something that can slow down your app. It can even make your app completely unresponsive. And garbage collection, sometimes, it's not as much now as it used to be, but Node.js have what's called a stop-the-world garbage collector, which means that it will pause everything that Node is doing while it's garbage collecting. But it also does this at the very last moment in time. So if you have enough free memory for your Node application, by default, that's 1.7 gigabytes. The garbage collector will not run. But if you run into the memory ceiling, for example, if you have a memory leak, or if you're running on a system that is only, let's say, half a gig, and you haven't configured your Node, probably the garbage collector will kick in all the time and try to collect garbage, and that might potentially slow down your app as well. So, as a promise, CPU-intensive code. That is synchronous I/O, talking to the disk, for example, synchronously, which you shouldn't do. JSON parse in some situations. Well, it's always synchronous, but in some situations, if you have a very, very large JSON object you're trying to parse, that will also slow down your app. Regular expressions can sometimes slow down your app. If some of you might not know this, but regular expressions in JavaScript can be susceptible to what's called a redos attack, where the time it takes to parse a certain string grows exponentially in certain tricky situations. Crypto, another example of something that takes a long time, that should be done asynchronously. Template rendering, and a lot of other stuff, because this is by no means a complete list. So let's look at how can we figure out what part of our app is spending too much time on CPU. So the answer is right here in these two emojis. It's called a flame graph. And a flame graph looks like this. Most of you probably have seen it, maybe. How many of you have seen a flame graph before? Okay. When I first saw a flame graph, it looked pretty and it was flames and stuff, but I didn't really know how to read it, how to use it to debug my application. So we're gonna look at that. So the question is, how can we know what part of our program takes us most CPU time? That's what we're gonna use the flame graph for. So the answer to that is we can periodically ask the CPU what it's working on. And that is also called CPU sampling. So CPU sampling is when you have a process running on the CPU, indicated by this time arrow here. Then you ask it, oh, what are you working on? And it's like, oh, I'm executing this function called foo. And then after a while, you ask it again, oh, I'm still executing a function called foo. It might be like the second time it run it or the fifth time it run it, you don't know, but it's working on the foo function still. Then you ask it again, and it's like, oh, I'm working on this function called bar, and oh, you ask it again, and it's now foo again, and then it's bar again. So now you have, like, for each period you ask the CPU what it's doing, you have the name of the function and some other metadata about the function. But you can also ask the CPU to say, oh, how was this function called? So you can get like a stack of who called that function as well. So it's pretty clever and pretty powerful. So you can get like a lot of basically stack traces, is what you end up with, of what the CPU was doing at these times where you were asking what it was doing. And you can do this on a production system. And then a flame graph is basically taking all these measurements, reorganizing them a little bit, and showing them in a graph. So you do like this. And then you have a flame graph. And what does that mean? Basically, instead of time being on the x-axis, it's basically just sorting the top frames that it was sampling alphabetically. So you have bar being first because it's first in the alphabet, then you have bas, then you have foo. And the size, the height of each flame is the stack size. So that's how many stack frames were beneath the function that you were sampling. And then the width of each flame is how much time our sampler, how frequently our sampler found this function on the CPU. And that's all there is to it. And now you know how to read flame graphs. So, but how are we generating them? How are we sampling? How are we getting the data to generate these flame graphs? The answer is Perf. Perf, it's a Linux tool. general purpose Linux tool that can sample what the CPU is doing. And a lot of other stuff. That's what we're going to use to sample our node process. So it's really simple. You write on your production system, you write perf, then you use the command record to tell it to record the profiles to a file. You tell it to, for example, sample at 99 hertz, so 99 times a second. It will ask the CPU what it's doing. And you give it the process ID that you want to sample. You tell it to get like the full stack trace and not just the top frame. And you tell it to, for example, run for 30 seconds. So that's like a reasonable size of sample that you didn't get by that. And what will happen is it will simply just create a file in your current working directory called perf.data. And perf.data will basically just be a list of all these stack traces that it collected. And then to view those stack traces, you simply just write perf script. And then you get like a lot of stack traces, which can be like, you can't really use that for anything. So you're like, what? Let's see here. Come on, there we go. OK, so let's zoom into one of these stack traces for a second. We see in the bottom here, we have some node internals, V8 and stuff. And then we go further up the stack, we have some unknown stuff, which is kind of weird. And that's the problem, because that's actually our JavaScript stuff in disguise. The reason why it's unknown is because perf doesn't know anything about JavaScript. JavaScript is compiled just in time. So the memory address that we see over on the left are all like moving all over the place. So it doesn't really know what's going on in these frames. It just know there are frames here, know which memory address are associated with each frame, but it doesn't really know much. Yeah, that's the JavaScript stack frames. So the solution to this is to ask Node to basically record a little bit of metadata, because Node knows a lot about our JavaScript code, right? So we run our Node server in production with --perf-based basic prof-only functions. And that will basically create like a map file between the memory addresses and the actual JavaScript code. And it will by default save that normally in the temp directory with the process ID of the process that Node is running. And then if we run a Node script again and look at it, now we actually get some actual JavaScript files here we can see that actually makes sense to us as JavaScript developer. But we still have the problem of we have like this massive list of stack traces. So now we're going to look at how we're going to deal with that. So let's see. There we go. So let's see if you can see this. So I'm running a server in a virtual box here on my computer, so I can just SSH into that one. Hopefully, there we go. Can you guys see this? Cool. And let's see here. So let's start our server. So in here we have a server.js, and let's start it with perf basic prof only function. That's a hard thing to say. And just run this in the background, and then go over here and then let's just fire a lot of requests against the server just to get some data. So we're firing a lot of requests against the server. Then at the same time, let's try to sample for 10 seconds our process here. So it takes 10 seconds. We're just going to do it 10 seconds. Normally, you would probably do a little more, but just for the sake of this demo, let's do 10 seconds. So there we go. And we can go over here and we can kill the benchmarking tool. That was not good. So actually, what I think we need to do for some reason, I think we need to just restart. So what happened was that for some reason our benchmarking tool could not find the IP of the server. So we're just going to restart the server. I think It was because I connected to a different network now. So let's just restart the server here. So what I saw was, I'm using a tool called AutoCannon to basically be able to just fire a lot of requests against the server, and it said it could not fire any request against the server, like there's 000 everywhere there. So that's an indication that just the IP of the server was unavailable to it for some reason. So this is why I should have slaughtered some goats before I started this talk. Yeah, demo gods, what are you going to do? And the server is supposed to start, and it's running. If this doesn't work, I have a backup plan. Don't worry about that. I'm probably not on the. Yeah, it's probably timing out on the network. I'm on the HolyJS network, but it's not allowing me. There's something with this network. So, but nevertheless, yeah. So that's how it is. So while it's trying to start, we're going to go in here instead. So I already have a solutions folder. Always have a solutions folder. So basically, what the perf command did before, if I actually was able to fire a request at it, it would have made this perf.data file in my current version directory on the server. Step number 2 is, of course, this is your production server. You want to get this off your production server and be able to analyze it on your dev machine. So you just SSH in and do whatever you do to get this file off the server. Before you do that, you convert it, you run the perf script command that you saw before. That just generated all this. Actually, that's the data you need to get off. You need to get all those stack frames off the server. So you put that into a file, you just redirect it to a stacks file, whatever, and that's the file you need to get off. So then you end up with a stacks.out file, or whatever you call it. And there are many tools to generate a frame graph based on this output. The one I'm going to be using is called 0x. And you just pass it -g and then gen and the name of your stack file, and then just output it to a flame.html file. Run this, and then you just open this in Chrome. And there we go. And so we have a flame graph as we saw before. And there are some really nice tools in this generator. So 0x is just one of the many generators. And there are many nice tools we can use to kind of visualize our flames. One of them is called Langs, which basically shows us, if we go a little bit up here, which in blue it shows us all like the native stuff of Node and V8. And then it shows us all the JavaScript stuff in orange. So even though there's, the goal here, of course, is to look for the widest graphs, because those are the ones that spend most time on the CPU. And there is, if you zoom out a little bit here, there's a huge chunk to the right that you might be tempted to look at. But that native code is usually something that's probably called by JavaScript code. So to help yourself out, you need to focus on the JavaScript code. So you can click on one of these to basically zoom in to only view that. And then on the right hand here, we see, okay, there's a lot of like really, really tiny flames. That looks okay because it's doing JavaScript, but it's doing it really, really fast. But then we have like these really wide graphs, wide flames. So something CPU heavy is going on there. So we can zoom in a little bit further on those. And we can see that they all end in this node crypto thing up in the blue, like the first blue line is node crypto. I don't know if you can see that, but you can see here node crypto. So it looks like, and it looks like it's all doing some crypto thing. Let's zoom out a little bit again. So we can use another one called tiers to show us kind of like a little bit more colors, and we can see, I don't know if the color is that easy to see here, but just below the orange there is a color that's my own code, and then below that there's all the node modules I have. So there's something in my own code just before before I hit the orange. And if you look at that, let's zoom into this one, for example, it looks like it's all on CPU.js line 21. So it's like it's all doing something on line 21 in this file. So let's look at the file. I accidentally renamed it since I did this solutions file, so it's called server.js now, but it should be the same. So if you look at server.js, oh, I even moved it around. I messed up. Don't worry about that. I can tell you where, if I did this again, if the server was actually running, it would be inside roots, and it would be here on line 12. That's what it's supposed to say. So you just get the function. You get like the top function that is doing that you're looking at the frame in the flame graph. But so you don't get the actual line where it's calling the next frame. So you have to hunt about a little bit. But we saw that it was doing something crypto, so that's like a hint. We saw that the next thing it was doing was crypto, and there we go. So we can look through our function. There's not a big function. We can see, is it doing some crypto? And yeah, it is doing some crypto. And line 17 is actually hashing our password. So this is a sign-up route for our web application, and it's hashing the user's password, and it's doing it synchronously, which is, of course, a very bad idea. So we should change this example to be asynchronous, and we will not. And then if we run the perf script again, we will not see those white flames. So before I continue, let me just see if I can SSH into the machine now. Maybe not. I could. Okay, that's cool. Okay, so to recap, you need to have a few tools installed on your Linux machine, on your server to do this. I just put them up here. As I said, I tweeted the slide, so you can find this information online. You need to run Node with this magic flag to be able to save the metadata to the temp folder, so it knows what these stack frames are, so it's not just unknown frames. Then you need to record using perf to the perf.data file. And the thing you didn't see before was that you didn't run perf script and then pipe that, so redirect that output to the file that you can then take down to your development machine, and then you can use 0x or any of the other tools on that to generate the flame graph. So any of the other tools, there are alternative flame graph generators. One is made by the guy I mentioned in the beginning of the talk, which is kind of like the de facto one that everybody's referring to. And then a friend of mine, Torsten Lawrence, I thought I should mention, he also made a really awesome one, which is called Flame Graph on NPM. So bonus tips for CPU-intensive code. There's this module called blocked that you can install, and it will notify you if your event loop is blocked. So basically, if your Node program is running something that is really CPU-intensive, and you just you just give it a callback, and it will call that callback every time it detects that it's blocked. But it won't really tell you why. So bonus tip number 2. There's another one called block trace, made by this guy sitting down there. And if you install that, and let's say we have a program like this that just have a timer that just spins forever, it's an arbitrary example. You run your Node program with this block trace in front of it, and it will actually just hold and exit the program, showing you a stack trace of where your program blocked the CPU, which is really, really clever. What I really want this tool to do, though, is be able to run this in production and not actually crash your server. That's kind of stupid in production. So you should open a pull request. That would be really cool. So next topic is post-mortem debugging. What happens? You have a server. It crashes. And then you're like, what the fuck? So the first step is here, like normally you look at the stack trace and you can just see, okay, cool, fix the problem, deploy a new version, everything is fine. But in certain cases, that's not possible. You look at the stack trace, you look at the code, and it's like, there's no bug there. And it might be because the user sent you some data that you didn't expect, but you can't see the data in the stack trace. The data is gone. So let's talk about reproducibility. What do we need to be able to reproduce this problem locally? We need to, of course, have access to the code. But we also need to have access to the state of the application when it was running and when it crashed. And then we also need to have access to the stack, so all the variables and the arguments passed to each function. So that's called a core dump. And we can actually ask Node to do that for us. I tweeted out, because I was so proud of my flame graph emoji before, there's like, I want a core dump emoji. And tweeted out, I couldn't figure it out, so a bunch of friends helped me, and they were really not like, they were like, what? No, I don't know. So if you have a good idea for a core dump emoji, you can tweet me. So you need to tell Node to make a core dump, and the way you do that, you run it in production with this flag, abort an uncaught exception. It was like, of course you would abort an uncaught exception. That makes no sense. Like, that's what it normally does. So it's named a little weird, but basically what he's doing is you're basically telling Node to, besides printing a stack trace, just write a core dump to disk, whatever was in memory at the time of the crash. And then you need to tell your operating system, if it's Linux, you usually do this. You say ulimit c and then a size of how big a core dump do you allow. Because if you just allow core dumps all the time in production, you might fill up your disk. So you should turn this on and off as you need to. You can set it to unlimited just to allow any size of core dump. Yep. And then when Node crashes, you get this. You get a core file in your current working directory, which a bunch of data, because it's basically just dumping all the memory of the process down into a file. So the next step, of course, is how do we look at this data? Enter a tool called MDB. MDB is a modular debugger that is really extendable. It's originally made for Sun Microsystems for Solaris servers. So you can't really install it on your Ubuntu machine. You can't really install it on your Mac or your Windows. So it's a little bit tricky. But we'll get to that. So using MDB, how do you do that? You need a Solaris machine. That's step number one. But it works on all the open source variants as well, so you might be able to get your hands on one. You need MDB, of course. Then you need, just as before with the stack traces, MDB doesn't know anything about Node, so you need a plugin for MDB. That's why it was modular. That's the M in MDB, to tell it how to understand Node or JavaScript. And Giant made that, so that's cool. You need the core file that is dumped on disk, and you actually also need the Node binary used to generate the core file. So when you get the core file, you need to get that off your machine, so that, including the binary running on the machine, to be able to debug this in a different place, because you don't want to do this on your server, of course. So you have your production server, and you have your Solaris box. On that, you install MDB, you install the MDB v8 plugin, then you transfer the core file, you transfer the Node binary, then you run MDB, you're golden. But again, the problem, how do you get the Solaris box? Luckily, some other friends of mine made this thing called Autopsy, which is basically a really, really easy way for you to run a Solaris box locally on your own machine. So the way Autopsy works is that it expects that you already have VirtualBox installed. So VirtualBox you can get for free from Oracle. It's basically a tool to be able to run any server on your own machine virtually. And then Autopsy will automatically create a virtual machine inside VirtualBox and install something called SmartOS, which is a hypervisor that allows you to run Solaris on your own machine or inside VirtualBox. And also install MDB and the MDB v8 plugin. So it's really cool. boxes and boxes and boxes. So, and you just SSH all the things down to that, and then you're good. So let's look at this. Let's hope my server runs again. It took a little while for it to fail on network connection, but I think we're good. So let's see here. What do we have here? We have a server. Okay. What did I say I needed to do? I need to, of course, run Node.js with this flag abort an uncaught exception. And it's crashing already. That's cool. It's because it couldn't find the crash file. It's because it's called server now. Okay, let's try again. Actually, let's just, no, it didn't make any. Okay, server. Oh, it didn't make a stack trace, a core file, because I forgot to set the ulimit. Let's do this. Ulimit C and then just unlimited. So now we told Ubuntu to just like allow any size of core dump. Now we're running the server. And then if, what did I say I wanted to do? Oh yeah, so I have a, let's try to sign up. This is an Express server that we can sign up on using a post request to a sign up page. I think I have, there we go. So I'm firing a request to it, to the sign up page. And of course, there we go. And it crashed. And if you look on the right side, it says core dumped. And then we look at the current working directory, we can see there is a core file. So something went wrong, obviously. Something failed when we tried to sign up. And we get a stack trace as well. We can see it crashed on, it cannot read property first of undefined. So let's try to look at server.js. What did it say? It said line 16. So let's look at line 16. So obviously, you can see we're trying to find user.name.first. So for some reason, name is undefined. But we don't know why, because it's supposed to be there. But maybe it's something with the data that the users end up. So oops. What? Happy. Tmix. Tmux. Demos. Demos are so hard. So so let's try to get the data from the server. Let's try to get the, didn't I have that somewhere? Let's try to get the Node.js file. That was like the binary that was used to generate the core dump. Let's try to get the core file. We get that off the machine. There we go. And now we just run autopsy and the Node.js file and the core file. And what it's doing now, it's saying, this is going so great. It is supposed to start up this machine. It's getting better and better. Let's do, so it's supposed to start this SmartOS thing automatically. Let's shut this thing down. So we can run autopsy status. So VM is up, so it figured out now that the VM is running. So let's try to run this again. I didn't run start. That was what I was supposed to do. I was supposed to run autopsy start. OK. So what it's doing now, it's basically talking to the VM, and it's taking our Node core file, our Node file and our core file, and it's trying to upload them, which is not going good either. Maybe it's because I started it wrong. But this is going great. Ew. Let's see. What we can do instead is we can just SSH into it, because I think I left connection. Isn't it running? Maybe it's not running. It has the same problem as before. For some reason, there's something with this network that it chimes out trying to get an IP. Oh, so now it's starting. I think we're good now. Let's try again. Yeah, there we go. So now it's uploading the node file and the core file, and then it's trying to connect to the MDB, trying to load the V8 plugin. And on some systems, this is actually an error I expected to happen. On some systems, it can't really connect to the MDB file. So that's actually cool that this actually happens here, and I expected this to happen because it's trying to talk with MDB over SSH. It's not bulletproof. I know the guys who made it, and they said pull request are welcome. So this allows me to basically show you how to do this yourself. So you basically just log into the, just need to log into the server here. There we go. Okay, so now we have the server, and then we look at the folder that we logged into, and those two files that we just uploaded are there. So we just run MDB manually. So this is basically what it's trying to do behind the scenes, but it's very easy to do manually. And then we just tell it to load V8. That's the V8 plugin. So now we loaded V8, the V8 plugin. So now it understands JavaScript. So the next thing we need to do is basically say, okay, let's look at the stack trace of the crash. JS stack. So we can see we have some native code that's like your Node and your V8 and stuff, and then you have a few JavaScript frames, three JavaScript frames there in the middle, and some other native code. And you can see it says unsave and stuff like that. So it knows it's JavaScript. But let's see if we can look a little deeper into this, because I mean this is basically just a stack trace we got before, so we're not really any wiser right now. So let's give the argument vn0. So now we actually see some more for each frame. We see the file. We see the line number where the crash was, and we see the value of this inside the function. In this case, on the top frame there, this was undefined. We see that it got two arguments, arg1 and arg0. The first was null, so it's probably the standard error that you usually pass to callbacks. And then the second one was an object. And the object was, if you remember the source code from before, the object was the user object that we were trying to do user.name.first, and that's why it failed. So the next thing, of course, is like, let's see if we can look into this object. So we can next to the object there is a memory address. So we can write the memory address here, and then JS print, and then we actually get the value of what's in the memory at that point in the core file, and we see that there is a JavaScript object that we expect with a property that have another object and first and last name. But we can also see that name is spelled wrong. So it's NMAE. So obviously there was a problem with the data that the user sent us. And this is not something that's possible to do by just looking at a stack trace. Obviously you could say maybe we should have a guard against this, but users might send us data that we don't expect, and there's no way of knowing this and seeing what crashed our system without looking at stuff like that. So now we can go in and maybe make a nice guard to make sure that if we get invalid data, we just tell the user invalid data. So to recap, you need to make sure that unlimited is set or any size. You need to start your server using abort and uncut exception. You need to run MDB with the node binary file from your production server and the core file, of course, and you can use these commands to kind of inspect what's going on inside the memory of where the process crashed. And there's some other tools besides MDB that works on more systems than just Solaris. So you can take a look at those as well. And at the bottom link there is a link to the Post-Mortem group under the Node.js Foundation that is actively working on making these things easier to do in Node.js. So I suggest to take a look there. And finally, memory leaks. So you have a a heap, and the memory of any node process looks like this tree structure. You always have a root node, and if you lose connection to any of the node, the garbage collector will find it and garbage collect it. So that's good. That's not a memory leak. What is a memory leak, on the other hand, is if, let's say, we are adding some kind of object to another object, looks like this, but then we keep adding these objects and we forget to clean the old ones up. Maybe we only want the last one. And as time goes on, like the memory usage of our node application just grows. So the question is, how can we figure out which objects are leaking? And the answer is, again, is heap dump diffing. So what is heap dump diffing? Let's say we have a running process, and at some point we ask the process to dump all the content of the heap in memory. And let's say it looks like this. Then we wait, 10 minutes, an hour, depending on how fast the memory is leaking. Take another dump, and then the idea is, of course, to diff these two dumps and figure out, oh, the green nodes were added, they were not there before. And then to look at the common ancestor of those nodes and figure out, oh, here we have a reference to these nodes, we shouldn't have that reference. So that's the idea. That's what we want to do. So this is your final demo. Hopefully it goes better, because I'm not using any server for this. So let's go in here. So let's start a server. So before I could do that, let me just show you that I installed a module here called Heap Dump. So the Heap Dump module will sit inside your server, and it will just listen for you to ask it to make a heap dump. It doesn't do anything besides that. So you install this in your production system, and you run it. You run your server. So now it's there, and now let's fire a lot of requests at this. So we are hammering the server with a lot of requests, and now we need to send this, or we need to just figure out what is the PID of this server, okay? And then we need to send a kill signal to that PID. It's not going to crash the server. It's just going to make the server make a heap dump. So let's take one. So now, actually, if you look at the current directory, there is now a heap snapshot in the current directory. And let's wait a little bit. And OK, this is good. Let's send another one. And you need to do this on your server, of course. And then look again, there's 2 heap snapshots. So that's good. Let's just dump this, stop. Good, OK. So the next thing is to take these 2 heap snapshots and open up your Chrome inspector that you all know and love. Oops, that's a little bit too much. Then you just need to load the 2 heap dumps. The first one. And the second one. In this case, I didn't wait that long, so you can see it only grew by 1 megabyte between the 2. And then you need to go and say, select one of them, and select comparison, and make sure that you selected the other one here. So now we have actually a comparison of the 2 and looking at only the differences between the 2. And then what you can do is you can sort by delta, and you can start looking at, so it will group all the objects that it found in memory, and say which of the ones did it find more of in the second heap dump compared to the first one. And we can start to look at some of these. Let's make this a little bit bigger. So if you open any of this up and look at this, we can see that, okay, this is a property called output on server response that is part of an incoming message. So this is HTTP related, and it's attached to a property in our system called active. And we can go through this, and as we see this, we'll see the same pattern. This is all related to server response incoming message. So in our case, we're leaking some request objects. If you go down here, there is actually an incoming message right here So this is probably the root cause. And you can see it's attached to this object called active. So if you go back and look in our server, oops, we can actually see that we have an active object, and we are adding request objects to it as to try to keep track of all the active requests. And it looks like we're cleaning them up down here by using delete whenever the request ends, but something goes wrong. Apparently, this doesn't always work. And I can tell you a spoiler in this case, it's because it's not always that request actually emits an end object. So if the client just closes the connection without probably ending, it emits a close and not an end. So we're missing that. So if the user just closes his browser or something. So we need to actually also listen for close. And that will fix this memory leak in this case. So this is like a way to diff and look. It's a little bit hunting for these things. It can take a little while. But it's a really, really nice way to figure out what is growing between. And of course, like if we had more traffic coming to our system from the time we took the first to the time we took the second, we expect it to grow a little bit. So you shouldn't treat it as everything that's growing is a memory leak, but it's a good indication. It's a good place to start. And instead of trying to have that problem, what I recommend you to do is using the EOS module end of stream that takes care of all of this for you so you don't get these memory leaks. But that's a whole nother story. So, and here's some recap slides. I'm not going to go through them right now, but again, they're on Twitter. And there's an alternative approach that is called gcore that you can use to take, if you can't install Heap Dump on your server, or you won't install Heap Dump on your server, you can use gcore instead, which will basically do the same thing, but it's from the command line. And I have a little cheat sheet here on how you can use that, which I'm not going to go into details in. If you want to talk to me later, you can do that. I'll happily show you how to use it. And that's it. Thank you.
We have time for a question or two, about 2 minutes.
Hi, thank you for your case, and I have a couple of questions about memory leaks in Node.js. First is what kind of preferred technology or technique for debugging and memory leaks in Node.js? And second question, what do you think about immutable objects in JavaScript? Because each change the object.
Can we take the first question first? Because it didn't quite. You're asking about memory leak tools.
What is the best feature for debugging?
The best feature for debugging?
Yeah, best tool or best feature or best practice.
Debugging memory leaks.
Yeah.
Let me answer that first. So using the Chrome inspector, as I showed you, I find it's the most easiest. Okay. But it has a lot of limitations. Where if you're using gcore, which you can basically point to any process on your system and say, make a dump of all your memory to a file. Then you can use MDB, as I showed before, to do a lot more crazy stuff. But it's a lot more advanced, something I don't have time to go into here. But I'll happily show you after. Does that answer your question?
Yeah, good.
And the second question was?
Second question, what do you think about immutable objects?
About?
Immutable objects.
Immutable objects.
I think it's resolved the problem,
I'm not necessarily. That's a good question. I don't know. I don't have an answer for you on that.
Because the links of memory is every time is new. Is a new object, and every time garbage collector know this object of previous state will be erased from the memory heap.
So you're saying it could help in some of these cases?
Yeah.
It probably could. I haven't really played that much around with it. But in any case, you will always have situations like this. I mean, immutable objects would not have solved this problem here, for example. You always have situations where you might keep something around, and the garbage collector doesn't know that it's not. I mean, there's still a reference to it, so I mean, it doesn't know that it can't garbage collect it because there is a reference to it, so it can't. So it's more like basically a bug in your code, right?